Believe it or not, everybody, we are already 8 units down and just a few more to go. Unit 9 is all about solutions. Before we get into too much about solutions, we definitely need to focus on one of the most common solvents that make up solutions, and that is water. Water is a remarkable compound on planet Earth. It is very, very unique. It has so many unique properties about it. One of them is its shape. Now, to draw the Lewis dot structure again, if you guys remember from last semester, we would have 6 dots around the H because of oxygen's in the 6th column of the periodic table. And then hydrogen would get 1 dot because it's in the 1st column. They would share. Remember, each of these bonds is a shared pair of electrons. And then oxygen would have 2 unbonded pairs. Now, because of that, it's going to be a bent shape. Okay, a bent shape because, of course, it is not linear. Now, it also has an uneven charge. So up here on the top would be the partial negative, and down here at the bottom would be the partial positive. That's because, again, oxygen is much larger. It is more electronegative. So the electrons of both the oxygen and of the 2 hydrogens will spend the majority of the time whizzing around the oxygen and very little time around the hydrogen nuclei. Therefore, the bottom part of my drawing is going to be a partial positive charge from the hydrogens of the the protons of the hydrogens minus their electrons. And then the oxygen will really have the 8 electrons the majority of the time, giving it, again, a partial negative charge. Now, because of that, it is going to be a polar compound. Polar, if you remember, means it's asymmetrical. The top is not symmetrical to the bottom. That's why we have an uneven sharing of electrons. So that is going to give it, a very unique property. Its polarity is very important. Its bent shape is very important. Now, because it is polar and because it is bent, it is able to form what we call hydrogen bonds. And hydrogen bonds, remember, are weak intermolecular forces that can be formed and broken very, very rapidly. And it's going to give another unique property to water. So the question says, how does the density of water in the solid state compare to the density of water in the liquid state? Now, what you notice right here on the image is the ice on the left is very geometrically structured. The water molecules are in these little hexagonal positions in 3 dimensions, whereas on the right side, the water is going to be much, much more chaotic. The water molecules will be moving around. They're going to be constantly breaking hydrogen bonds and making hydrogen bonds and then breaking them just as quickly. And so that they're really moving around, which again is why it's a fluid, right? That's why it's able to pour and move and travel in the way it does. Whereas solid water is going to be much more fixed and very, very solid, right? So therefore, the density of the solid ice is definitely going to be less than the density of water. And again, that's really kind of different. Most things are not that, don't work like that. Typically, when you make a solid, the molecules get closer together, they get fixed in position, and they cannot move very much. Again, that's what we typically think of as a regular solid. Then when you melt it into the liquid state, then they would start to move further apart and are able to slide around each other, giving them their fluidity. But for ice, it's the exact opposite. And again, this is interesting because ice is less dense, therefore ice floats. Now, I know you guys know that ice floats, but how many other things do you know that in the solid form would float on top of their liquid form? I'll wait, but I can tell you, I don't think you know of any. Like I said, this is very, very unique. Now, the density of water is 1 gram per milliliter. And then the density of ice is 0.9 gram per milliliter. And that's interesting because, again, if we have, say, here's my ocean and here's my iceberg, we would always say, and again, this is my iceberg. Let me label that because I don't want to confuse you guys. All right, so what we have right here, again, this would be about 10%. Why can I not do those little brackets? Let's see, let me try it again. This would be about 10%. And this right here would be 90%. So whenever we say the tip of the iceberg, what we literally mean, and I know we don't actually use it to this strict of a meaning, but what that literally means in science is that there is 10% that is always visible and 90% of the iceberg would be not visible. So again, that explains why the Titanic hit icebergs. If you see it, there's 9 times larger underwater that you cannot see. It's the same thing if I put ice into a glass of water. There would be 10% above and 90% below. Okay, that's again another unique property of water. Another one is its high specific heat capacity. You're going to learn about this in 2 units from now, or 2 or 3 units from now, when we get to thermochemistry. The specific heat capacity of water is very, very high. What that means is that it takes a lot of energy in order to heat up water, and it takes a lot of energy to be lost in order to cool down water. This is why it takes so long to heat water up when you're trying to cook. Everything else is, gets hot really quick, but that pot of water, man, it takes quite a while for it to heat up, and it takes a long time for it to cool down, which is quite, again, unique for a liquid. Another interesting thing about water is its weight. It is quite heavy for a water. It's about 8 pounds per gallon. So for every gallon of water, that is 8 pounds. That is really, really quite heavy for a liquid. All right, moving on to the notes. Again, it says, why is water called the universal solvent? That is because it is able to dissolve most ionics, most ionic compounds, and most polar covalents. So what does that leave? That only leaves non-polar covalents. So the majority of ionics, the majority of polar compounds can dissolve, which is a lot of things. The only thing it cannot dissolve ever is the non-polar covalents. Non-polar covalents will not dissolve in water. So water is a very, very, very good solvent, very good at dissolving things. In fact, that's why drinking pure water is not good for you, because pure water, pure H2O with nothing else dissolved into it, is not good for you, because we as a species have evolved on a planet where pure water, pure H2O is impossible to find. The only way to make pure H2O is to do it with a very good filtration device. Other than that, we have never encountered it as a species. We have to make it. So drinking pure H2O is actually really not good for you. If you guys remember about osmosis, it basically will leach water out of your cells. But anyway, it's not good for you, because again, water is so good at being a solvent, at dissolving things, that we never encounter that unless we buy a filter. So moving on. So it says right here that why does water's shape make it such a good solvent? And again, that's really because of its polarity. Remember, its polarity is because of its bent shape, like this. That's what it looks like. And remember that it has the partial negative up here and a partial positive down there. If you guys remember that symbol, that's a lowercase delta in the Greek language. This right here means partial in science. It's not a full charge, it's a partial charge, okay? That makes it so good because, again, that makes it able to dissolve ionics. Remember, ionics are made of ions. Ions are positive and negative. Well, a water molecule has a negative region and a positive region. So if it is a charged compound, it will dissolve in water. And the fact that it is polar also makes it a good solvent, because anything that is also polar will dissolve in water. Again, the only thing that will not is a covalent that is non-polar. Covalent, again, are not ions, and it is not polar. Therefore, it cannot dissolve in water. Now, this rule that we often say is like dissolves like. Now, what that means is basically anything that is polar will dissolve in something else that is polar. Something that is non-polar will also dissolve in something that is also non-polar. So polar dissolves in polar. The word solvent, which more about that word in the next video. I've already used it a few times in this video. And likewise, a non-polar will dissolve in, whoa, I put pulvent. That's funny. Let me fix that, because I'm sure you guys noticed that, and I did not. In a non-polar solvent. So like dissolves like, meaning polar dissolves polar, and conversely, non-polar dissolves non-polar. Now, this cartoon at the bottom is a very good way to explain this. So this little polar bear, he's saying he's dissolving into the water because, again, the water is polar, and he's a polar bear. And yes, I know it's a joke, but it's you get the idea. Whereas this black bear here, or brown bear, grizzly bear, whatever he is not worried because, again, he's not polar. Therefore, he's not worried about being dissolved. Again, like dissolves like. Polar dissolves polar. Non-polar dissolves non-polar. Okay, this is, again, the reason why oil and water do not mix. Oil is non-polar. Water is polar. Polar does not dissolve nonpolar, okay? Like dissolves like. All right, guys, that gives you a good intro into water. And like I said, there's so much more to learn about water. The more you learn about it, the more interesting it becomes, and the more you learn how unique water is. But as always, guys, thank you for watching.